Okay. Hi, everybody. A very good evening. I hope everyone of you is doing great. Right. Okay. So I think we have enough number of people. We can start. Let me share my screen. Okay. So we were doing aldehydes and ketones, right? Aldehydes, ketones, and carboxylic acids, right? Okay. So last class we were solving some questions, right? We will solve some more questions, but I think before that we will try to complete this acid part also. Okay, we will try to complete the carboxylic acid part and then we will solve some more questions. Okay, right. So now starting with Ipac naming, right? How do you name these acids, right? All that you have to understand is there is no prefix for COOH, right? Because that is going to be the maximum prioritized functional group in all of the organic chemistry, right? That is going to have the maximum priority. All right. Okay. So because of that, obviously you're not going to have any prefix. If at all any other functional group and so carboxylic acid is there, obviously any other group is there, but irrespective of that, COH is going to get the maximum priority. Okay, but they will have the suffix, obviously, right? And the suffix for them is going to be oic acid. Okay, right? So we'll just do very simple examples because you already know how to work with your secondary suffix, primary suffix, what are the different prefixes, everything you already know, right? We'll just quickly do this. Say for example, this is a very bad diagram. Okay, say I have this one and this one, right? So you understand that when they can give you like this also, it means what? C double bond O and OH are on the same carbon atom, right? That is nothing but COOH, right? So we'll start numbering from here. 1, 2, 3, 4, 5. You have to include the carbon atom which is there along with C in the COOH, right? That has to be included. All right. Okay, so 1, 2, 3, 4, and then the fourth carbon atom, we understand that there is a ketone, right? So then obviously for ketone, we would have used the prefix, and for acid, we will use the suffix, right? So first you can write the root word. We know root word is going to be divided by the number of carbon atoms in the chain. So that is going to be 5. So the root word is pent, right? And you understand that there are only C single bond Cs. There are no C triple bond Cs, no C single bond Cs, no secondary mean. Secondary suffix is going to be AN, right? Because only single bonds are there, right? And then in the first carbon atom, we have oic acid, right? That I told you that should be the suffix, right? Oic acid is the suffix, and before that the prefix should come. And I know for ketone, what is the prefix? Ketone prefix. Sorry.
ONE ends with ON.
That is ONE is suffix, right? What is prefix? What is the
alkyl?
Alkyl.
Sorry, alkane.
Alkane. No.
E is eliminated.
Huh?
E is eliminated.
Alkanoil. Okay, it's not alkanoil. No, not alkanoil. So like from other like,
oxo.
That's the one we commonly use, right? Hope you remember. Oxo, right? So whenever there is one ketone and there is another group which have more priority, say there's an aldehyde or say there is an acid, right? And along with it, the ketone is there. For ketone, we are going to use prefix, and the prefix is going to be, prefix is going to come before the root word. Whenever you write the compound's name before the root word, that is your prefix. So prefix here is going to be oxo or keto. You can also use keto, KOKETO. That is also fine, right? Fine. So in the fourth carbon atom, we have a ketone. So it is 4 oxo pentan 1 oic acid. You don't have to mention this if it is only 1, right? Okay. Other than that, everything is going to be simple. Maybe we'll just take something like this. Okay, we'll include more also. Fine. Okay, this should be enough, right? Fine. So I have can I do this quickly? Like, will not take much time for this, but 1 minute I'll give you. Quickly name this. Yes, done. Shouldn't be taking this much time. Yes, any answers? Or you need more time?
Sir, is it 3 hydroxy 1,5 pent dipentanoic acid?
Okay. What about the double bond? How will you mention pent? What?
2
Ah,
dioic acid. I'm
okay.
not sure how to.
And yeah, you're almost right. Almost. Okay, we'll see that. So people. So we have again two ways of numbering. So that is 1, 2, 3, 4, 5. Or you can go from here. 1, 2, 3, 4, 5. Right? Okay. Now the first priority obviously go to COOH. That's however you go, it's going to be 1, 5, 1, 5. That's not an issue. So now you're looking at the second priority, right? So we have COOH, we have double bond, and we have OH. So obviously maximum priority goes to COOH. The second priority goes to OH, not double bond. Okay, the second priority goes to OH, right? And surprisingly, what are you seeing is that either you go from top 1, 2, 3, 4, 5, or from here 1, 2, 3, 4, 5, all you're getting is 3 for OH. So that also does not matter, however you mention, however you go for numbering. But the third priority, again, now is going to decide where how we are going to number, that is a double bond. Right. Now double bond has 2 from this side and 3 from this side. So obviously we'll choose the lowest possible number. So we'll take 2. So we have to start numbering from 1, 2, 3, 4, 5 like this one. Right. So once the number of carbon is done, you can write pent. Right. And then you understand that in the now the secondary suffix. After this, secondary suffix should come. So that is where the double bond or triple bond or single bond that you mentioned. Here it was what? And because only single bond was there. Here I have a double bond, so it is going to be 2. And you have to mention where it is present also, right? And then you understand that in for first position and in the fifth position, we are going to have carboxylic acids. So continue after that, the primary suffix 1, 5 dioic acid, right? And before that, you write the prefix of OH, and that is obviously going to be prefix of OH, prefix of OH.
3 hydroxy.
Hydroxy, right? You have to be keep on in touch, like or else you'll forget. Okay, so it is 3 hydroxy. Okay, so if at all only alcohol was there, then how to written this? If at all the COH was not there, only these are hydrocarbon and only with OH was there, then what I should have ended up with? I'm asking the suffix. What is the suffix for OH? What is suffix for OH? If at all you have to write suffix for OH, what will you write? Really? Just because you studied that in term 1, so I'll not remember. It's OL, right? OL, all. Right? So for OH, it is OL. For alcohol, for aldehyde, what is the suffix? For aldehydes, what is the suffix?
AL.
It's AL.
AL. At least that for this term I'll remember, sir. Okay, good enough. Okay, fine. So again, then for ketones, someone already told, but they told it for what is that prefix? The suffix is ONE, right? For ketone, the suffix is ONE, right? And you have to remember the prefix part also for some of them. Okay, right. So these kind of things, I think you'll be able to do. Like if you just have to know what is the prefix, what is the suffix, rest of the rules and all you already know. If you just remember the prefix and suffix and how what is the order you write them. First is prefix, then root word, then secondary suffix, then primary suffix. Right? That this order you remember, and what are the names of suffixes, secondary suffixes, and primary suffixes you remember. That's it. Any compound given, you'll be able to write. Okay, fine. So then, well, let's see one more thing. Like how this whatever I'm going to do now, the same kind of problems we faced with CHO also, that is your aldehyde also, right? Same kind of problems we'll face here. For example, say I give this one. Okay, now what will you name this? How will you name this? Do you know? Or any guesses at least, even if you don't know?
Benzoic acid.
Huh?
Benzoic acid.
If see, generally I do this. Okay, whenever I am teaching offline classes, right? Whenever I generally teach offline classes, and someone says cyclohexane as benzene, the first thing that will happen, this dust would have flown from here to your head. Okay, how many times I have told that only if you put some circle or you mention the double bonds, then only it is benzene, or else this is going to be what? This is going to be cyclohexane, right? Right? These kind of silly mistakes we should not do, right? Okay, fine. How do you name this? Tell me. Benzoic acid means I would have had this one, like one circle here or three double bonds I mentioned, that would have become benzoic acid. Okay, now I have cyclohexane ring, so that will be called as
Cyclohexanoic acid.
that's what we expect, right? Cyclohexanoic acid, that's what we expect. Same thing happens with your this thing also, that is your CHO. How do you expect? Oh, what is the name of this? Someone?
Cyclohexanal.
That is what we expect, right? So we expect. It is very surprising that nobody remembers. Okay, if I tell you cyclohexanal is not the name, then at least will you remember what happened? How do you know how you should name this? Nobody remembers.
The carbohydrate.
At last someone. Yes, right. Okay, how do you name this now? Tell me.
Sir, because carbon is attached to this.
No, I'm not asking you the explanation. What is the name? This compound. What is the name now? What you told is correct. How? Complete it fully.
Hexane 1 carbohydrate.
Hexane. It is normal hexane or what hexane?
Cyclohexane.
So almost right. Okay. So this one is going to be called as cyclohexane because again, why and? Because again, there are only no double bonds, only single bonds are there. Okay. So cyclohexane carbaldehyde. This is how we write this. We don't write this as cyclohexanal. That is not correct. Why is it like this? Is it because if you write cyclohex, if that was the root word, that means here I'll have only 6 carbon atoms. Correct? But look at this. In this compound, I have 1, 2, 3, 4, 5, 6 in the ring, and 1 carbon atom is there in the CHO. Also, totally 7 carbon atoms are there. Right? So if you write cyclohexanal, you're referring only for 6 carbon atoms, but in the compound, actually, we have 7 carbon atoms. So that's why we write cyclohexane, 6 carbon atoms. If at all you write only al, it does not make sense, right? Because that means it is included in the chain, but it is not. That's why we write carbaldehyde, that is representing 1 carbon atom, which is there in the aldehyde. That's how we write it. Okay. So we could have done the same thing for this also. CHO, CH, CH, CH2, CHO. Right? Now, how did we name this? Someone remembers? The same thing has to be done, right? Because the same problem you will face. Like, say if you go in this direction, you will not be able to account for this particular CHO. If you go, say, in this direction, you will not be able to account for this CHO. If you go in this direction, you will not be able to account for this CHO. So what I'm trying to say, like, however you're trying to start and end, somehow or the other, you'll be missing 1 CHO from the main chain, right? So again, in these cases, you have to, I think you remember how to do this. Right? Anybody remembers what is the name of this compound? How do you name this? Again, you have to use carbaldehyde here, obviously, to overcome this particular problem which I told you. Right? We have to use carbaldehyde. Okay, I don't know. Like it is like this. Right? So what we have to do is you have to forget that these 3 are there first. Like forget that the CHOs are there. Think how many carbon atoms. Other than that, how many other carbon atoms?
Each 10 1, 2, 2 tricarbohydrate.
1, 2, 2 or 1, 1, 2.
So 1, 1, 2. Sorry.
Right. Okay. So anyways, so people who still don't remember how exactly I'm going to do. So it is going to be, you have to forget that the 3 CHOs are there, and other than that, see how many carbon atoms we have. We have only 2 carbon atoms, right? Other than the CHOs, the CH and CH2 are the only other 2 carbon atoms. So take only that first. So if you write that, you'll write ethane, like how you write cyclohexane, thinking about this particular group, right? Say like cyclohexane group, right? So ethane. Now take the numbers. Now you have to start numbering from this carbon. Only the carbons which you are taking, that only have to number, right? 1 and 2. That's it. Okay. The first carbon atom 2 CH2, 2 CHOs, and second carbon atom 1 CHO. So we write 1, 1, 2. We have to use carbaldehyde because you cannot write al. So in this case, it is going to be tricarbaldehyde. Okay, right? So now the same kind of problems you will face with your carboxylic acid also, right? So now how are we going to name this? We will name this as, first is same, cyclohexane, right? And whenever you are not able to include the COOH into the main chain, we will, like just like carbaldehyde, we'll be using carboxylic acid. As simple as that, right? Carboxylic acid. Okay, cyclohexane, carboxylic acid. Okay, say another problem will do something like okay, like previous one only will take, but this time a little more. Okay, go for this. This one. So just instead of carbaldehyde, since we have acid, you should use carboxylic acid. That's the only difference here. Yeah, I think we have to increase the number of classes. Like, I don't know, for the past 1 month, we have been doing 1 chapter only, right? Aldehydes, ketones only we started. And maybe some classes we missed, but irrespective of that, I think we are going little slow. Right? Where are you in mathematics and physics? How many chapters completed in term 2? Guys?
So in physics, 3 chapters.
Physics 3 chapters only left. Okay,
No,
3
sir,
chapters
almost 3 chapters finished.
Okay, mathematics?
I am not in maths, sir.
Okay, someone in mathematics can tell me how much is completed?
We finished one and we are doing the next one.
Okay, now only 1 chapter is completed. Okay, how many total chapters are there in mathematics for term 2? Same as physics and chemistry, 6, 7, something like that only is there, or more than that, or lesser than that?
5, 6.
5, 6.
I think it's 6.
Okay, so similar to this thing only. Okay, so that means we are little lagging behind, but math is giving us company. Okay, fine. We'll see. Like if at all, I can just include the number of hours. But the problem is, like already 11th, I'm taking 2 hours. Okay, and for 11th, Sunday, I will not be able to do that because Sunday, right after your class, their class starts. That means if I have to extend your class, I have to postpone their class also, and it will be too late. Already I finished at 1:30. It will become again half an hour, and after that break will include so much time. So Sundays will not be able to, but this Fridays, that is normally when we meet on Fridays, those can be made into maybe a 2 hours class. That is possible. And maybe in some other day, in another day, if at all you are free, maybe we can have 1 hour class. Maybe in the mornings, maybe whenever you're free. Right? We'll maybe fix a timing. They'll speak to you. I'll speak to the management. They'll speak to you. We'll come up with something. Okay. Right. So anybody got the name? This one?
Is it ethane 1, 2, 2 tetracarboxylic acid?
Yeah, good. Correct. Right. So it is ethane. Again, same thing. Right. Forget that these 4 are there. Don't think about it. Now you have to consider only these two carbons. How many are there? 2. So it is ethane, right? And in the first and the second only 4. 1, 2. In 1 and 2, both they have 2 carboxylic acids. So it is going to be tetra carboxylic acid. Yes, that's it. Okay. So like this, any kind of compound given to you, you will be able to, in any kind of acid or any kind of aldehyde, ketone, or matter, any compound, as long as you know the suffix and prefixes and the Ipac rules, you are set to name any compound for that matter. Okay, right. So that is about the Ipac naming. Right. Now moving on to physical properties. Right, we saw about physical properties of aldehydes and ketones. Now we'll see what happens. Right. Obviously, I know that we know that we'll be studying 2 things under physical properties. One is boiling point or melting point. Right. The other one should be solubility. Solubility in water. Generally, that's what we speak. Right. Okay. Fine. So now, yes, 3 conditions or 3 parameters you will check for considering boiling points. If I give you 2 compounds, 3 compounds, and ask you to arrange them in the order of boiling points, what are the parameters you will use? 3 parameters. What are they? Three parameters for say comparing boiling points. What will you use?
Sir, the structure of the compound.
Structure of the compound. No, is that the criteria we look for? Okay, if you just look at the structure, how will you tell? Okay, this is going to have more. This is going to have more boiling
If
point.
it's a spherical structure, it will have a lower melting point.
What structure?
If it has a spherical structure, it will have a low boiling point.
Okay, fine. Somewhere, okay. But is that what we studied? Anybody else remembers 3 points? What did we study?
The number of carbon atoms.
Number of carbon atoms. Okay, I can accept. That then. But that means basically number of carbon atom means I can like I think that you're telling.
The intermolecular forces.
Yes, intermolecular forces. Yes, makes sense. That's the whole point, right? Basically, say I want to go from gaseous state, which is going to be a little very far away from each other, right, to liquid state. Sorry, I'm running the exact opposite. Right, we are going from liquid state. The particles are very close by, right? Okay, now I'm going to gaseous state in which I have to increase the distance between the particles. So here they will have very strong force of attraction. Here they'll have less force of attraction. So I have to supply energy. To make sure that they go far away from each other. Right. So obviously, stronger the force, right? The stronger the force, higher will be the temperature, or higher energy should be supplied for you to separate them. Right. It's all about always the intermolecular forces, right? But indirectly, how do you check for intermolecular forces? Right. Like that's where this 3 comes, right? First one is molecular mass. Second one is branching, right? And the third one and the most important one is extent of hydrogen bonding. Right, extent of hydrogen bonding. These 3 are the criteria you will be using for almost all of them. All right. Okay. I mean, for aldehydes and ketones, we even go for dipole interactions. Basically, everything. Like let me tell you, dipole interactions. Right. So these 3 are actually everything somehow also relates to the strength of intermolecular forces. The strength of intermolecular forces, and it is somehow related. Whatever we are telling, molecular mass, branching, extent of hydrogen bonding, strength of dipole interactions, all of them eventually speaks only about these intermolecular forces. Okay, so these 2 are directly intermolecular forces. That is, hydrogen bonding is one type of intermolecular force. Dipole interaction again is going to be one type of intermolecular force. Now, this dipole-dipole interaction is what is going to be existing in your aldehydes and ketones. Hope you remember, this will be happening only for polar species. Hope you remember. So I had that polar bond in your C double bond O, another polar bond we had in another C double bond O was there. So whenever we have polarity, what is going to happen? The more electronegative atom will have del positive, and the less electronegative atom will have del, the most electronegative atom will have del negative, and the less electronegative atom will have del positive, right? Carbon in this case is less electronegative, so del plus, right? Okay, so now you're going to have an attractive force between this molecule and this molecule. How? We have a del minus here, we have a del plus. The attractive force is here. The dotted line which I'm representing here is what is your dipole-dipole interactions, right? Okay, so that we saw in your aldehydes and ketones. And obviously, please understand that the hydrogen bonding is stronger. Hydrogen bonding is stronger than dipole-dipole interactions. Okay, so if at all, that is the reason why. That is the reason why when we compared, say, RCHO with RCH2OH, or say RC double bond OR ketone for that matter, right? So almost you can see only one hydrogen is different. Okay, two hydrogen is different. The molecular mass is not that different, right? The molecular mass was almost similar only, but still the alcohol was actually winning, right? The alcohol was actually winning. They have higher boiling point because of what? They have only dipole-dipole interactions. Which one? The aldehydes and ketones. But your alcohols will have hydrogen. Right, so hydrogen bonding is stronger than dipole-dipole interaction. That's the reason why we say alcohols are going to have more boiling point than corresponding aldehydes or ketones. Right? Okay, fine. So we'll just summarize all the points one more time. Right? So boiling point is going to be directly proportional to the molecular mass. You know why? More and more molecular mass, more and more stronger van der Waals force. I think when we spoke about this van der Waals force in the last time when we talked about the boiling point of aldehydes and ketones, I explained you what exactly is van der Waals force. Just because of electrons moving, we are going to have some force, right? You can just go through the notes or go look at the video recording, something you can do, right? Okay, and then next thing is branching, right? That is inversely proportional to branching. So in the sense that if I have something like CH3, CH2, CH2COOH, right? And with CH3, CH, CH3, COOH. This is CH3, right? Okay. Now both of them have same molecular mass, 4 carbon atoms, everything same. Hydrogen atom, oxygen atom, everything same molecular mass. But you understand that this has more branching because you understand that there's a branch, right? So there is more branching here. So it will have less boiling point. Right, so the boiling point would be higher for this, right? Okay, because it is having more branching. Why? Because branching, if it increasing, the strength of the van der Waals force decreases. Okay, if branching increases, the strength of the van der Waals forces increase. Branching increases, strength of the van der Waals decreases. So we can tell it is again going to be directly proportional to van der Waals force. Right, but van der Waals force is inversely proportional to the branching, so that's why boiling point is inversely proportional to the branching. Okay, so highly branched systems will have lesser boiling points, as simple as that. Okay, and the last and final one, or the second last one, that is extent of hydrogen bonding, is obviously going to be directly proportional. Right, and at last your dipole-dipole interactions, again more and more dipole-dipole interactions, more and more boiling point. Okay, now keeping all this in mind, right? So we can maybe check, like first if we start CH3 COOH with HCOOH, if I compare, right? CH3 COOH with HCOOH, if I compare, which do you think is going to have higher boiling point? Which will have higher boiling point? Come on, guys. You know the criteria, right? You know how they're related also, right? Well, which is going to have higher boiling point? What is the criteria now? You have to use any one of them, right? What is the thing you have to do? Molecular mass, or say this is what is your number of carbon atoms, basically. Right? More the molecular mass, stronger the van der Waals force, higher the boiling point. right? So out of these two, whichever is going to have more molecular mass is going to have more boiling point. Okay, which is the answer then? Which is going to have higher molecular mass, or which is having higher number of carbon atoms? Really? You guys don't want to answer? It is because it's a very easy question, or something is there in the chat maybe. Okay, it's just the previous things. Yeah. So what I'm asking is, out of these two, which is going to have higher boiling point? CH3C over H, HC over H. Now this has more number of carbon atoms, right? This has more number of carbon atoms. This has only one carbon atom. This has two carbon atoms. So definitely this will have more molecular mass. So this is now going to have more boiling point because it's having higher molecular mass. This is having less molecular mass. Right? I don't know what is happening to you. Okay. Next, the branching we saw, right? How branching happens. Now these two, right? These two are going to have same molecular mass. You can see if you look at the formula, it will be C4H578, C4H8O2. For this also the formula is C4H8O2, right? That means both of them will have same molecular mass, right? But in this case, now what you have to look for? You have to look for branching. Right now, this has branching, this doesn't have branching. The one which is not branched will have higher boiling point. Right. So the first criteria we look for is molecular mass. Right. Then if you have two isomers, that is obviously different branching. Right. So same molecular mass but different isomers means you have to look for a branched one. The branched one will have lesser boiling point. Non-branched one will have higher boiling point. Right. And the third one. That is your extent in this extent of hydrogen bonding. Okay, first question again. Hydrogen bonding. For hydrogen bonding to happen, what are the two things we require? Tell me. For hydrogen bonding to happen, what are the two requirements? A compound can show. So this compound can show. Sir, how will you tell? Like based on what? Can show hydrogen bonding. Can have hydrogen bonding. How will you tell?
Hydrogen should be bonded to an electronegative
Okay, that is one criteria.
atom,
So,
like oxygen fluid
like
and nitrogen.
okay, oxygen. Can you just tell me the elements again? What are the elements?
Oxygen, fluorine.
Oxygen, nitrogen, and fluorine. Okay, right. So the first condition, right? The first condition is that we should have something called as hydrogen donors. Right now, these hydrogen donors, what she's trying to say, right? There should be a hydrogen atom attached with a highly electronegative element, right? And these electronegative elements can only be three. That is oxygen, nitrogen, fluorine, right? So in the compound which you're checking, whichever compound you're checking, if that compound has a OH bond or an NH bond or an FH bond, any of these three bonds are there, then directly you can tell that will be showing hydrogen bonding, because the other criteria is that we need to have something called as hydrogen acceptors also. Now that's very simple. Hydrogen acceptors is something which should have lone pairs on them. Right? Hydrogen acceptors are the one which is going to have lone pairs on them. But the moment you see any of these kind of bonds, right, they will have both hydrogen donors as well as hydrogen acceptors, because I know oxygen will have two lone pairs, nitrogen will have a lone pair, fluorine will have three lone pairs. Right? So the moment you see these kind of bonds, right, you can decide for sure that this is actually going to show hydrogen bonding. Right? So in carboxylic acids, right, we know that we have, this is the structure of carboxylic acids. Right? Obviously, there is another thing coming. Right? So the only difference between aldehyde, ketone, and a carboxylic acid is C double bond is common. Right? But in case of aldehyde, we write one side hydrogen, another side carbon. Right? And in case of ketone, we write both side carbons. Right? And in case of carboxylic acid, we have one side OH and the other side can be either hydrogen or carbon. Doesn't matter. If you have hydrogen, there is only one possibility, HCOOH. Right? But carbon, if you have, many other possibilities can come. right? So you understand that here C double bond O, OH. Now you see this OH bond present. Is it not? You see this OH bond present. So definitely in your carboxylic acids, right, we are going to have hydrogen bonding. Okay, carboxylic acids are going to have hydrogen bonding, and because of that reason, right? Because of that reason. Okay, so for example, I want to compare CH3OH with, or not CH3OH. We'll come to this later, right? Say I want to compare, or before that, we'll try to understand how I can show the hydrogen bonding. Right? Let me show the hydrogen bonding for you. Say I have this COOH, right? We have the COOH. Okay. Now we understand that this hydrogen is going to have a del plus, and this oxygen is going to have a del minus because of the same reason, difference in electronegativity. The electron cloud will be more towards your highly electronegative element. Oxygen is more electronegative, so the electron cloud will be more towards oxygen. That's why it's having a partial negative charge, and the opposite for hydrogen. A high electron cloud is moving away, so it will have a partial positive charge. Right? Okay. Fine. So let me take this one molecule. Another molecule will take. Right? So you can have C double bond O. OH, again another bond. Right? Now again what will happen? You will have a lone pair, or say del negative on this and del positive on this. Right? So you can have an attractive force between the partial positive charge, and the lone pair, because lone pair is again negative charge. Right? Or you can say that I'm going to have interaction between this del positive and this del negative. But the correct way is to look for the lone pair only. The attractive force between your del positive and the lone pair is what is the best way to represent it. So you can put a dotted line like this between the lone pair and the del positive. Now this is one molecule, another molecule. They're very strongly attracted to each other with the help of hydrogen bonding. Right? And you can also represent, look at this. C double bond O, OH is there. Right? And say I have C double bond O, OH is there. This is going to have del positive, this is going to have del negative. Right? Now you understand that this is del positive. I don't have to take the lone pair from this oxygen only. Here we took it from this oxygen, right? I can have a lone pair on this oxygen also. I have actually two lone pairs on this oxygen also. So you can show the hydrogen bonding between this one, that is the lone pair on the carbonyl oxygen, and the del H plus. That is also hydrogen bonding only. So I can have two different hydrogen donor sites. Sorry, hydrogen acceptor sites. This is your hydrogen acceptor site, right? In this case, this oxygen is your hydrogen acceptor site. Hydrogen donor is the same. Obviously, the OH bond attached wherever it is there, that is your hydrogen donor, right? But whichever is donating the lone pair, involving the lone pair, that is your hydrogen acceptor. So in this case, this oxygen is hydrogen acceptor. In this case, this oxygen is your hydrogen acceptor. Okay. All right. So now we understood that there can be hydrogen bonding, and we now understood how can the hydrogen bonding exist also. Okay. Right. Now, if so, every car. So fine. If I compare CH3CHO, or let me. Okay, fine. CH3CHO with CH3COOH. Right. I want to compare their boiling points. Now we know that in CH3CHO there is no hydrogen bonding, because there is no OH bond, there is no FH bond, there are only CH bonds, right? So no hydrogen bonding, and obviously I know this has hydrogen bonding, no doubt about it, right? And this I know in case of your aldehydes and ketones, we have only dipole-dipole interactions, that also we know. But dipole-dipole interactions are weaker compared to hydrogen bonding. So we can tell that the acid will have more molecular mass than your aldehyde or your ketone for that matter, anything for that matter, aldehyde or ketone. Right? So we understand that the acid will always have higher boiling point than the aldehyde or ketone. That is always true. Okay. Now next point is if I compare alcohol with acid. Okay, two carbon, not number of carbon atoms is not changing much. Okay, so we have alcohol and an acid. Now you understand that here also I can have OH bond, right? And here also I have OH bond. So both show hydrogen bonding. Right? Both of them show hydrogen bonding. Now how will you decide? Now how will you decide which is going to have higher boiling point? Can you guess? Okay, can we go to the chat box and put your guesses, people? This is carbon, this is compound number 1, this is compound number 2, which is going to have higher boiling point. Both of them have hydrogen bonding. You need not be right, you need not be wrong. You can just put the guesses, 1 or 2, which is going to have higher boiling point. I'm looking at the chat box. Okay, these two are the compounds. You have to comment for. Go for it, people. Type 1 or 2, which is going to have higher boiling point. It is just a guess game, just to make you participate. Just go for it. Go on, people. I'm telling you, just a guess. Everybody can go and put your answers in the chat box. Yes, one answer came. Go for it, people. I have 13 people here, and for 1, 2 responses, this will be the case. Go for it. Go for it. Everybody, put your answers there. 1 or 2, which will have higher boiling point. Who answered? Okay, Devesh said 2. Okay. Fine, we will everybody. Akshay, Anandita, Anirudh, Satyapriya, Ananya, Suryamuthu, Ashik. Suryamuthu only answered here. No, that is Devesh, right? Yeah, people, go for it. Put your answers in the chat box. 1 or 2. Okay, Nandakishore says 1. Go on. I just want to know what you think, right? You need not be correct. You will not be wrong. Doesn't matter whether you're right or correct. Right or wrong, sorry. Okay. Yeah, we'll come to that point. Yeah, actually, we can say that, yes. Yes, Devesh. We can say that. Okay, fine. So a few responses came. Okay, Ananya, good, 2. Right? Okay. So fine. As I told you, both of them show hydrogen bonding, right? Both alcohol and your acid, both of them indeed show hydrogen bonding. There is no doubt about it, right? But the thing is, whichever is going to show stronger hydrogen bond, that's what you have to check, right? Whichever is going to show stronger hydrogen bond, that is the one that is going to have more boiling point. Because we said here, like, look at this. Where is it? For boiling point, we said extent. Extent means what? Strength. Right? Strength of hydrogen bonding is the criteria. Right? Whichever is going to have stronger hydrogen bond, that is the one that is going to have higher boiling point. Okay. Right. Now, people, we have already established this fact that here also I have OH bond, here also I have OH bond. So they have almost same hydrogen donor capabilities. Correct? Because this is going to have a del plus, this is going to have a del plus. Both of them have same hydrogen donor capabilities. Okay, but what about hydrogen acceptor is the question, right? Now you see here, right? We saw here also. Now you see there can be 2 hydrogen accepting sites, one coming from the OH oxygen, right? The other hydrogen acceptor can be coming from where? From the carbonyl oxygen, the C double bond, that oxygen, right? But in alcohol phosphorus, there is only one oxygen atom. Right? So that oxygen atom can only act as hydrogen donor. I mean, in the sense that the hydrogen atom can act as hydrogen donor and the oxygen atom attached to the hydrogen can only act as hydrogen acceptor. In the sense that this has only one hydrogen acceptor site. Right? But this one has 2 hydrogen acceptor sites. Right? So that is the reason why this will show stronger hydrogen bond. Right, and this would be a weaker hydrogen bond, and that is the reason why this will have higher boiling point. Right, so compared to almost all the functional groups, right, compared to alcohol, compared to any other functional group you take, acids are going to have comparatively very, very high boiling points because they have very, very, very strong hydrogen bond. Okay, this you have to keep in mind. Acids will have almost compared to all the functional groups, acids will have one of the highest boiling points because of very, very strong hydrogen bonding. Right? Now that is also okay. Now we have compared aldehyde or ketone with an acid wins. Alcohol with an acid wins. Now what if we compare 2 acids? right? Two acids, now we know what are the criteria you have to use. If two acids are there, you will go for molecular mass. Whichever is going to have higher molecular mass will have higher boiling point, right? Now, if at all, you go, another thing you can go for is branching, right? If one is going to have lesser branch, the other one is highly branched, the one with no branching or lesser branching will have higher boiling point, right? Now, you can also say like this way, right? What you can tell is the number of carbon atoms. But if it is too much, okay, like how can we? No, we don't have to go for that. Yes. Okay. Now, two things. So let's go for molecular mass and branching. Okay. So that is about your boiling point. Okay. Done. Now, the next thing what we'll do is we'll take up solubility. The second, right? The second physical property is solubility. Right. And we all know the famous mantra, right? We all know that like right, like dissolves like, right? So in this case, we don't have to follow that. Now the thing is, say for example, acid as well as water, right? Both of them can show hydrogen bonding, right? Both of them can show hydrogen bonding, right? So because of that, I can have hydrogen bonding between these two also, hydrogen bonding between these two also. So because of that, the COOH acids are very highly soluble, very highly soluble in water, right? Again, why? Because of hydrogen bonding, right? Hydrogen bonding not with acid with acid. Hydrogen bonding can be formed between what? Between your acid and water. Okay, between the acid and water molecule, you can have hydrogen bonding. That's why the moment you try to dissolve them, they'll have strong attractive force and it will completely dissolve. No issues at all. Right? Okay. So these are the things you have to know about the physical properties. Okay, physical properties of acid, that is boiling point, melting point. The second one is going to be solubility. You have to just remember that we are going to have high solubility for high solubility of acids in water. Right. Now, what if we compare? What if I compare two acids? Okay, fine, they have hydrogen bonding, so they will be highly soluble. But what if I compare two acids now? Say if I want to compare HCOOH and CH3COOH, I want to compare their solubilities. Okay, right. So let us again take a vote. 1, 2. We have already done these kind of stuff in alcohols also, in aldehydes, ketones also. So remember, try to remember it and tell me which one will be more soluble in water. HCOOH or CH3COOH, compound number 1 or compound number 2, which will have higher solubility in water. Go to your chat box and you can put your answers. 1 or 2. 1 is HCOOH and 2 is CH3COOH. Again, so it's just a guess game. You don't have to worry about whether the answer being right or wrong. Yes, one answer came. Okay, Ananya says 2. Anandita says 2. Okay, I don't know. This was, I think it was Ananya's previous thing. Okay, fine. Anandita only answered now. 2. Okay, Devesh says 2. Okay. Yes, anybody wants to register their answers, go for it. Ananya says again 2. Okay. HCOOH, that is 1. Okay, fine. Fine. Okay. Anybody wants to give an explanation of why did you choose 2 or why did you choose 1? Or maybe we'll start with the minority. I think it was Nanda Kishore. Oh. Yeah, Nanda Kishore, you told it is HCOOH. Any this thing? Why did you say that? Or was just a guess?
Sir, because HCOH has a lesser number of carbon atoms.
Okay, fine. So because of that?
So it's highly soluble.
Okay, no, that is not the entire reason. So I don't think HCOOH will dissolve in water. Oh, okay. It does not dissolve at all. Okay, that is one answer. Fine. So because of the number of carbon atoms, how is it that the solubility is getting affected? That's what I want to know. That is very easy. This has one carbon atom. This has two carbon atoms. If the number of carbon atoms increases, why is it the solubility is changing? Increasing or decreasing, we'll first understand later. But why is it that the number of carbon atoms has some role to play? How? What? Okay, so people, right? It's all about being more polar and less polar. Okay, we know that the length of the carbon, right? We know that the length of the carbon chain, right? Length of the carbon chain, right? More and more as the longer the length of the carbon chain, less and less will be the polarity. Because your hydrocarbon part, your carbon chain is actually hydrophobic. I don't know whether you remember this. Right? Your carbon chain is going to be hydrophobic. What do you mean by hydrophobic? They hate water. They repel water. Right? I don't know whether you remember cleansing action of soaps. How do soaps clean the dirt? Right? They have something called as hydrophobic part. They have something called as hydrophilic part. They're actually made out from this carboxylic acids only. Okay, the soaps and detergents, if you can remember. Okay, the salt of the carboxylic acid. So they will have a part which will have hydrogen bonding with water. So they'll have very strong attractive force. On the other side, you will have the carbon chain, which is going to be hydrophobic, which is going to go away from water. So like that, what you can do, you'll be able to remove the dirt with the help of these hydrophobic and hydrophilic interactions. Okay, anyways, so more the number of carbon chains, more is the non-polar nature, or say more is the hydrophobic nature, or I can say less and less polar the molecule becomes. It is going to have lesser and lesser polarity as the length of the carbon chain increases, because that is hydrophobic, because it is non-polar. All those are connected. Right? So what you have to understand is the length of the carbon chain, polarity. So definitely it is going to be inversely proportional to solubility in water. Solubility in water. That means higher the carbon number, higher the carbon chain, less and less will be solubility, because if the carbon chain increases, hydrophobic nature increases. Right? They're going to hate water more and more and more if more number of carbon atoms are there. Right? So we can blindly say that HCOOH will have more solubility than in the case of CH3COOH, because this is going to be less polar. Right? Or I can say it is going to be more hydrophobic. Right? And these are the reasons. I can say this is more polar. This is more hydrophilic, I can say. More hydrophilic. Philic means loving, nucleophile. Are you able to hear me now, guys? Okay, I think I went out because I didn't go out. I was thrown out because my laptop, the laptop got switched off. Okay, so I'm back. So who's the host? Can someone make me the host? Oh, I'm the host still. Okay, good. Fine. So I will share my screen again. Okay, fine. So we decided that The acid, which is going to have lesser number of carbons, will be more soluble. As simple as that, because more the carbon chain, more will be the non-polar nature, less will be the polar nature, less will be the solubility, because it is going to be more and more hydrophobic. Okay, done. So that is all about your physical properties. Solubility done, and your boiling points done. Right, now what are we going to do? We are going to see how are we going to prepare carboxylic acids. Okay, how are you going to prepare carboxylic acids? Can you tell me already existing methods? You already know some methods from the chemical properties of alcohols, from the chemical properties of aldehydes, right? You already know certain things, right? How and all you can prepare? Can you tell me? From alcohols, how can you prepare? You already know this. Say now, okay. If at all you tell me that's it was last term. Okay, from aldehydes, how do you prepare acids? From aldehydes, you can prepare acids, right? How can you prepare? Really? One simple reaction, right? Tolerance test, Felling's test, all those are giving why. Why that is happening? That is the clue I can give you. What does PCC do? PCC? What does
Weak oxidizing agent.
Wow, okay, good. So basically, so what do you have to do? Where do you use PCC? Weak oxidizing agent is very correct. Okay, fine. Where do you use it?
For converting alcohol to aldehydes.
For converting alcohol to aldehydes. Okay, makes sense. Makes sense. Right? Okay. So we understand that. Say, okay, look at this, people. Alcohols. If you oxidize alcohols, we are going to get aldehydes. Okay. When we oxidize aldehydes, we are going to get acids. Okay. Right. Obviously, we're talking about primary alcohols only. Right. Primary alcohols will get oxidized to aldehydes. What will happen to secondary alcohols if I oxidize them? People. Secondary alcohols, if I oxidize, what will happen? What will I get on oxidizing secondary alcohols? What is it? Ketones. Yes, right. We'll get ketones. Okay. Anyways, so primary alcohols we oxidize, you're going to get aldehydes, and aldehydes you further oxidize, you are going to get acids. Okay, right. Fine. Is there any direct way to get acids from alcohols rather than going to
strong oxidizing agents like KMNO, acidified KMNO?
Yes.
Or
Good. Very good.
K2CR2.
Good. That is also fine. Right. So we'll be able to convert alcohols directly into acids if you use very strong oxidizing agents. Right. And strong oxidizing agents are only two. The moment you see strong oxidizing agents, these two should come into your mind. KMNO4 and K2CR2. Okay. Right. So like if you have alcohols and if you put KMNO4 or K2CR2, there is no aldehyde in between now. Directly you'll go to acids. Okay, but if at all you want to do this conversion, now you have to use weak oxidizing agent, and weak oxidizing agent example can be what? PCC. That's what I said. Pyridinium chlorochromate. You'll be able to convert an alcohol to your carboxylic acids. Sorry, to your aldehydes. Sorry. Right. Okay. Now, how do you convert aldehydes back to aldehydes to acids? How do you do that? Right now, here you can use strong oxidizing agents, no doubt about it. As to alcohol itself, if you put strong oxidizing agent, you are able to convert it. Right. So here also you can go for KMNO4, K2CR207, all this stuff. Right. Directly you can use. Right. PCC you cannot use because PCC is only capable of oxidizing alcohols. They don't oxidize aldehydes. But if you use KMNO4, K2CR207 and all, they're already strong. So if they're able to go oxidize alcohols to acids, definitely they'll be able to oxidize aldehydes also to acids. That's okay. Right. So that is the first method of preparation. First method of preparation is by oxidation of alcohols. You can take maybe the first one, right? Oxidation of alcohols. What do? Say I have RCH2OH. That's a primary alcohol I'm taking. Especially I'm taking only for a primary alcohol. Now say if I put KM4, I am going to convert this into 2 O's. Right. I'm going to convert this into RCOOH. Right. Okay. Now that is it. So if at all you take any examples, you have to take only primary alcohols. Be very careful. Say if I have CH3CH2OH. Now same thing. KMnO4. I put. Okay, I put KMnO4. So what is going to happen? You have to convert this COOH part into COOH. CH3COOH. That's it. Okay, so with this part, CH2OH part will convert it into COOH part. Okay, CH2OH part converted into COOH part. Okay, right. Next, same thing you will be able to do with respect to your aldehydes also. From aldehydes by oxidation of aldehydes also you can take. Right. So again, what you have to do? Same thing only. You have to use the same oxidizing agent only. Say in this case, you use K2Cr2O7. Right. So now what you're going to do? Convert that CHO into COOH. Okay, CHO to COOH. Right. Say if at all we take any proper examples. Let me take benzide. I mean, what is this? Benzaldehyde. Now tell me this is benzaldehyde. Okay, I'm putting a circle. Right. Okay. So that is benzaldehyde. Okay. Now to this benzaldehyde, say I go for KMnO4. Right. Now we'll be able to convert that CHO into COOH like this. Right. Very simple. CHO wherever you see, convert it and put it as COOH. Right. Okay. So these two methods, I think you should be knowing already. Okay. From us, like because you're like actually. Right. Any other thing other than K2Cr2O7 from the alcohols chapter? Do you remember? From alcohol, sorry. From the aldehyde part, do you remember? Is there any other way of converting RCHO to RCOOH? Do you remember any other way? I gave you one clue in the starting of this question when I asked you this question. How can you do this? I gave you some clues, right? What clue did I give? I told you some tests. What happens there? What test did I talk about? People, before like 5 minutes, before explaining this oxidation of alcohols and oxidation of aldehydes, and I started this, you can do like this and all, right? We spoke about this. How do you convert aldehydes to acids?
Hydroform test.
Hydroform test is one thing. Okay, fine, definitely, because that is going to have lesser, one carbon atom less. Okay, that is a very good method. Okay, you will be able to convert both ketone as well as aldehyde into acid with the help of hydroform reaction. But the only problem is that will be given only by C double bond O CH3. Compounds are going to have C double bond O CH3. Right. Other thing is one in the acid which you're going to form. Right, you're going to get one carbon atom less. Right, because one of the carbon atom would have gone as hydroform. Okay, right. So hydroform reaction has its own problems. First problem is that one carbon atom less is coming. Right. If at all you want specifically that only, well and good. Why not? You can use that. You want in the conversion they're telling convert maybe propanone. Convert propanone to ethanoic acid. Right, what will you do? Obviously, you know that propanone is nothing but CH3COCH3, right? You are going to convert it into CH3COOH, one carbon atom less, right? So what you should do? You should go for hydroform reaction. Right, CH, not CHI3, NaOH plus I2. Right, what will happen? One of the CH3s will get converted into CHI3, right? And the other entire one, the CH3CO part, you write it like that only, CH3, C double bond, you write, you just remove the CH3 and put what? OH. That's it. You have converted propanone to acid. That is ethanoic acid, one carbon atom less. Okay, and obviously you will be able to use only if you find these kind of groups, that is C double bond CH3 should be found out, then only you will be able to do this. Okay, that is one good thing. Okay, any other thing, any other test? which we used where we converted aldehydes to acids? Really? You don't remember? What other tests, at least do you remember what other tests and all we saw? What are the names of the tests? We saw one is Hydroform Test. Okay, in that chapter, what are the tests we saw? Tell me.
So
Tolerance, spelling.
Okay, tolerance, Felling's test. These three are the only tests we saw. No other test we saw. Like actually, there were one more test. Do you remember bisulfite test? Do you remember the name at least? Bisulfite. Okay, fine. If you're not remembering, I'll give you the notes. You check. You go to your book and check. Anyways, so okay, what happens in tolerance and Felling's test? Okay, give me 1 moment. Okay, right. So yeah, what happens in tolerance test? What happens in Felling's test? You are going to use, okay, first describe tolerance test for me. Tell me anything and everything you know about tolerance test. Go on. What and all you remember about tolerance test? Tell me. It's the only word I remember, sir. Nothing else I remember. Is it? Check your notes. If you're taken down notes, check your notes. See what happens in tolerances and tell me. Let me know. Quick, people. Go for it. Turn your notes, turn your pages, or turn your book, something you do, and let me know at least 1 point from each of you, at least. And that's what I expect. Go for it and tell me what and all you remember, what and all you know about tolerance test. Okay, well, it is a test for what? First question. If you ask me maybe the right question, at least you'll answer. It is test for what? It is test for what? What functional group can you test with it? Really? What functional group? Say if I give you
aldehydes to carbox.
Sorry?
Aldehydes to carbox.
Thank you. Right. Obviously, it is used for test for aldehydes. Only aldehydes will give this test. Okay, fine. Now, how do you, with the help of tolerance test, how do you confirm? By seeing what do you confirm that it is an aldehyde? What basically, how do you do the test? And the test, every like how you have to do it. And when you do it, what is the result that you see? And you see that, okay, sir, this is aldehyde only. How do you say that? I think this chapter would have been over in most of your schools, right? And I also told you so many times, we solved questions also. When we solved questions, I think you prepared and came, I guess. That's why I told no, like we solved questions. Yeah, you prepared and came, that's why you remembered. Now you didn't prepare at all, that's why you don't remember. Right? Go back and check tolerance test, people. Tolerance test, what do we do? Right? First, tell me.
Ammoniacal silver nitrate.
Right, that is the tolerance reagent. Right, the tolerance reagent is what? Tolerance reagent is ammoniacal silver nitrate. Ammoniacal silver nitrate. Okay. Now, what happens in this test? We have the CHO, that is the RCHO is there. Right. Now, if I put the tolerance reagent here, to add 2 to 3 drops of tolerance reagent, what is going to happen? In tolerance reagent, we have this Ag plus ions, right? Understand that? You remember the tolerance reagent exact formula? Ag, NH3 twice plus. This was the exact formula for tolerance reagent. Okay, anyways, so here you will have Ag in the +1 form, right? So now what is going to happen? I told you this tolerance reagent is a mild or weak oxidizing agent. This is what we have been seeing, right? This tolerance reagent is a mild oxidizing agent, right? So what is it going to do? It is going to convert your aldehyde directly into your acid. It is going to convert your RCHO to RCOOH, right? And in that process, what is going to happen? This Ag plus, which is present in the tolerance reagent, will form Ag precipitate. So this is how you confirm. You will form what? You will form silver mirror around the sides of the test tube, right? You will see that the silver is getting deposited, precipitate, right? You will see the silver precipitate only in the test tube. You're going to have aldehyde. If at all any other functional group is there, you will not see the silver mirror. And if at all aldehyde is there, you will see the silver mirror, and you can confirm, okay, it is aldehyde only. Okay, but in that process, what are you doing? In that process, you're actually converting your aldehyde into acid because your tolerance reagent is a mild oxidizing agent. Okay, so another method of converting aldehyde to acid. This we already saw again. Okay, fillings. Okay, what happens in fillings?
We use sodium potassium tartrate as a reagent.
That is the only reagent. Fillings has two things, right?
And aqueous copper sulfate.
Right. So we have two fillings reagents, fillings A, right? And we have fillings B, and together if you mix, you are going to get the fillings reagent, right? Fillings A is what is your aqueous copper sulfate. Fillings B solution is what is your sodium potassium tartrate. Sodium potassium tartrate. Right, so you mix these two, you're going to get your fillings reagent. Okay, what is going to happen? Again, only aldehydes will give this test. Ketones will not give this test, or any other functional group will not give this test. So when you put your fillings reagent here, what is going to happen? Again, the same thing is going to happen because again, your fillings reagent is a mild oxidizing agent. Right, it is a mild oxidizing agent, which is going to convert your CHO to COOH, or say RCHO to RCOOH. So what is happening in that process? In that process, you have your Cu2 plus ions in the form of copper sulfate, right? In the form of copper sulfate. Now those will get reduced to copper oxide, which will be in +1 oxidation state. Okay, and I know this one is going to be a red color precipitate. Right, so when you have a test tube, you add 2 to 3 drops of fillings reagent. If you find red precipitate coming, you can confirm that okay, that is an aldehyde. Okay, ketones will not give this test. So in silver intolerance test, the end point, how do you find out, is with the help of silver mirror. In the case of fillings, how do you find it? With the help of red color precipitate. Okay, right? So these are the different ways by which oxidation aldehyde can be converted into your acid. One is through KMNO4, right? The other one is through iodoform, right? And the other one is through your tolerance reagent and fillings reagent. That also will be able to convert your aldehydes directly into acids, right? And alcohols again directly can be converted into acids using KMNO4, again strong oxidizing agents, KMNO4 and K2CR2O7, right? Okay, people, I think we'll stop with this for today. Okay, so like next class, I'll be keep having more amount of reactions. What are the other methods of preparation, right? And then we'll move on to the chemical properties, right? So maybe
Sorry, I asked you a doubt last class, sir. Whether aldehydes are more polar than
yes, that's a good question. So ethers are the ones going to have going to be more polar. You know why? So the thing is, if we have a C double bond O, right? Whenever we have this double bond, that is going to decrease the polarity. Right, whenever we have C double bond O, the double bond decreases the polarity. Right, if you want to understand how, right, see, we have a single bond. CO single bond will have del plus del negative. CO double bond also will have del plus del negative. That is okay, right? Both the amount of charges will be same only, right? But the polarity of the compound is actually decided with the help of something called as dipole moment. This is the physical quantity. Okay, that the polarity, how much polar, if you want to compare two polar substances, which is more polar, which is less polar, right? That is going to depend on obviously the dipole moment. Okay. Now dipole moment is a physical quantity, right? Dipole moment dm, dipole moment is equal to charge into distance, right? First, what do you mean by a dipole? That I already told you. Some plus q minus q separated by some distance, right? This particular arrangement is what is called as a dipole. Okay, right. Now, dipole is the arrangement. Dipole movement is the quantity, physical quantity. That is the formula. This is the formula for dipole movement. What is a dipole? Dipole is equal and opposite charge separated by a distance. Okay, so the dipole moment formula is q into d, right? That means how much amount of charge I have into the distance of separation. What is the distance between them? Okay, now when you consider C double bond O and C single bond O, what is happening? The charge, this is your minus q, this is your plus q. This is your plus q, this is your minus q. Separated by a distance between the two atoms, right? So that's why I'll be able to call these molecules as dipoles, first of all. First understand that. Del plus del minus separated by some distance, because between the atoms there'll be some difference. The bond length per se, right? So that is exactly, that makes it dipole. Okay. Now, whichever, like the amount of charge, that is q value is going to be same, right? The q value is going to be same. But what about the distance? Now this is a single bond. This is going to be a single bond, so that means longer distance, right? Longer bond length, or say longer distance, whatever you want to call it. Right? Here it's a double bond, that means stronger bond. That means the atoms will be very close to each other. So this will have a smaller bond length. Right? Now Q values are same, del and del only, right? But the bond length, that is the distance between this value, the D value, right, is actually higher for what? For higher for C double bond O than your C single bond O. C single bonds are very shorter, so there they will have more dipole moment because they have larger distance between the two charges, and they will have less dipole moment. Right? And now I told you more and more, whichever is going to have more and more dipole moment, which will have more polarity, right? And whichever is more polar, obviously will have more boiling point, because the dipole-dipole interaction, the strength of dipole-dipole interactions also increases when I have more dipole moment. Okay, right? So that is why we have ethers to have higher boiling point compared to your aldehydes or ketones. All these reasons, right? First thing is dipole moment. What is dipole moment? I have to understand what is dipole first. What is dipole moment? That I have to understand. Q into D is what is dipole moment, right? Higher the, longer the distance, higher will be the dipole moment, higher will be the polarity, higher will be the boiling point. As simple as that. So CO single bonds are longer and double bonds are shorter. So they will have lesser boiling point, lesser, dipole moment. That is, they will have lesser dipole moment. And so they will have lesser polarity. And so they will have lesser boiling points corresponding to your ethers. Yes, understood?
Yes, sir. But in the book, it's given as aldehydes are more polar than.
Aldehydes are more polar than ethers.
Yes, sir.
Last time.
On example questions, sir. That's
Okay.
why I'm asking.
What is the reason they are giving?
It's a compound named butanol. So they are comparing butanol with epoxy thing.
Okay, fine. No,
So
it is an example question. So they are given the answer, right? Okay, study the
yes, sir. They said that they are butanol is more polar than ethoxyethane. Therefore, the intermolecular dipole-dipole attraction is stronger in former.
Okay. Okay. Now then I think you have to speak like this. When they say the dipole-dipole interaction is stronger, see, we have CH3OCH3, or let me take CH3, CH2, O, CH2, CH3, and we have CH3, CH2, CH2, CHO. Right. So it's all about, again, here I'm going to have del positive, del negative, right? And say we'll put it as del 1 and del 1. Here it is going to be del negative and del positive. This is going to be del, let me write it properly, del 2 negative here and del 2 positive here. So which will have higher del? Okay, depending on the groups present, right? Okay. Now in this case, we understand that this is an electron donating group. Both of them are electron donating group. right? In this case, we have electron donating group from this side. I know all alkyl groups are electron donating in nature, right? So when they are going to be electron donating in nature, I already have a partial negative charge on this carbon, on this oxygen, right? So I would say in both the cases that oxygen del to negative value increases here, right? Why? Because they already have having negative charge, and the electron donating groups will increase the negative charge because they are already negative charge. I mean, electron means negative charge donating to them, so the amount of negative charge will increase. Right now, here I have only one time increase, but this del negative will increase 2 times. Why? Because both side I have your electron donating groups. In this case, I have only one electron donating group. Right. So obviously, what will happen if I compare del 1 negative and del 2 negative? Right, del 1 negative is greater. This one, that is the ether's del 1 value is greater. Why? Because I have electron donating group increasing the negative charge. So electron donating groups increases the negative charge. Right. So now again, I can say this is whenever I have more charge, that means more polar and thereby higher boiling point. Right. So this consideration, see, when you in general consider this. Right now, they will. This is how we generally consider this. Like when you have no other groups attached, no other things are attached, only C double bond O, C single bond O is there. Definitely, you can speak like this. But if at all groups are attached, right, you along with the C double bond O, you have some other thing. Along with C double bond O, you have some other thing. Based on what is present, then like that, you'll be able to speak. Right. So this is how you'll be able to speak. This is going to have more positive charge. I mean, there are more negative charge than this. So this will be more stronger dipole than this one. Yes, that's how you can speak. Okay. Okay, I think Nandakishore was asking, right? I don't know. Is it fine? Okay, right, people. Is there any other question anybody has to ask? Okay, fine then. Thank you so much. We'll meet again next week. Tomorrow there is no class. Okay, I'm sorry. Sunday there is no class. I think you would have gotten the information by this time. We'll be compensating it very soon. Okay, right, people. Thank you so much.
Thank you, sir.
Thank you.